and the phase velocity. Okay, what is the difference between the growth velocity and the phase velocity? The growth velocity is a velocity with the overall shape of the wave's amplitude, which was known as the modulation or envelope of the wave propagate through the space. And the function omega, which gives omega as a function of k, is known as the dispersion relation. Okay, I think I have prepared the simple. Okay, can you see here, this one? This is a dispersion wave. That means that you can see that this dot actually change the wave. This dot can change the wave. Okay, it's interact with wave, the wave become longer. At first, these two waves have the same wave packet, but then after it go through this dot, you can see that the wave has actually changed. So omega can change k, k can change omega. Okay, this is what we call dispersion relationship. But then if it's not dispersion, if omega and k don't have any dispersion relationship, then you can see that when the dot go through this wave, it doesn't change. Okay, it doesn't change the wave, so it doesn't interact. Omega doesn't interact with k. Okay, this is another example to explain what is growth velocity and phase velocity. So see, when growth velocity and phase velocity are the same, then you can see that the blue one actually goes with the wave. But then for this one, the second one, okay, you see that the phase velocity is larger than the growth velocity. So you see, at first the blue dot is at front, but then after that the red dot actually pass through the blue dot. Blue dot represent the big packet. Can you see that this blue packet, the big packet wave, the wave packet, blue, because it's the growth velocity. But then the phase velocity, the individual one. So you can see the individual one actually faster than the growth velocity. Then this one, for the growth velocity equal to 0, you can see that the wave packet doesn't move. The wave packet doesn't move because the wave packet, the growth velocity equal to 0. Okay. And then for this one, phase velocity equal to 0, you see that the position of the red dot doesn't move. The phase velocity doesn't move. But then the big packet, the wave packet, the blue atom or the blue dot actually moving. So now I believe you have more idea on what is phase velocity and what is growth velocity. If you still not understand, I would advise you to get some reference lah. Okay, I'm not going to explain more because you have studied this in solid state physics, not solid state physics one, but I think 106, not physical ZCT 106. Okay, so from this equation, can we plot it in the graph? Can I plot it in the graph? Plus minus Ka over 2 sine Ka over 2. So like this, something like this, right? But then there's no way that we can negative omega. So the negative side, we take it out. So we only have positive omega. So when we plot in the graph, you get something like this. Okay, why? Because from this equation, we have positive, negative sign, negative sine wave. But we know that there's no way that can omega equal to negative something, right? In the real world, there's no negative omega. So this is the graph that we obtain. Okay, and this is actually omega over omega max versus sine Ka over 2. Okay, Ka over 2. So you can see this parameter is omega over omega max, and this parameter is pi over 2a based on this one. Pi over 2a means what? Is it a real space? No. If it's a real space, then we use a, 2a, 3a. But now it's pi over 2a or 1 over 2a. Then this is the reciprocal space. Remember that? Reciprocal space. right? For the cubic, if real space is A, then the reciprocal space become 2 pi over A, right? So the first Brillouin zone is 2 pi over A, which is from pi over A to minus pi over A, and this range is 2 pi over A, okay? And this is the first Brillouin zone, all right? So now we consider two conditions or two situations. The first situation is this section, okay? The second condition is the rest, okay? So we start from this section. For this section, Ka is very small, okay? K is very small. For this section, you see the value of K is very small, right? So K times A also become very small. So for this region, this is the region for long wavelength. While long wavelength, K is very small, means K equal to 2 pi over lambda. That means that lambda is very large, right? I repeat, now we want to look at this graph from two perspectives. One is from this section, the other from this section. For this section, we know that K is near to 0 and K equal to 2 pi over lambda. When K equal to 0, that means that lambda is very large. So Ka is very small. So when K is very small, then we can rewrite this equation equal to Ka over 2. Okay, if you don't believe, you just take out your calculator. You find the solution for sine 0.0001. You get the answer at 0.0001. Therefore, we can say that sine K over 2, when K is very small, we can assume that this term equal to K over 2. Okay. So when we assume this one is K over 2, then we just take out this one, we direct omega over omega max equal to Ka over 2. Okay, so omega max equal to this one that we have derived previously. So omega equal to this equation, and omega equal to this equation, then omega over K equal to V, right? So V naught equal to this term. Okay, I repeat, for the first region that K is very small, then we can rewrite sine Ka equal to Ka in this equation, or the complete equation in this one. This is the complete equation. So we just take out the sign. Okay, when K is very small. So now we just solve the equation. We solve this equation, then we get omega equal to this one. Okay, when we get this relationship, we also know that omega over K, we just move the K to the left hand side, then we get A square root of mu over M. And then we know that omega over K equal to V. So this is the phase velocity of this case. So V